The last set of notes in this unit is about some more applications of matrices. I have decided to cut the first application that appears in this set of notes, which is cryptography. It is a cool topic, and it's used everywhere. But like with matrices, we unfortunately don't really have time to even really scratch the surface of that topic. So I think just to ease the online transition, I'm going to cut it from this class. But in the handwritten notes that I'll be posting with this lecture, you can read over these examples if you're curious about them. But I don't intend to give you any homework or quiz or exam questions over encryption or cryptography. So you can ignore that for now. That means that the only application that I really want to talk about in this section is called Leontief input-output analysis. And let me, before we get into the details and the matrices, let me just scroll back up to this page and maybe make up a small example. So I'll give you sort of a one-dimensional example. Let's say that you are producing, I don't know, oil, something like that, and you want to get a certain amount of it to the market. I'll call that amount D. So that's the amount that we want to make it to the market. That D I'm thinking of as being demand. So we know that there's a certain market demand for our end product, and there's a distinction between D, the amount that actually makes it to the market, and X, which is the amount that we produce, because we are going to use some of our own product in order to get things to the market. So maybe you're going to use some of your oil or whatever. So maybe we'll say that you're shipping gasoline or something like that. You're going to use some of your own product internally as you deliver to all of these different sites. So maybe let's say that you're going to use 1/10 of a gallon for every gallon that actually makes it to the market. Then in that case, what you would have is, if X is the total amount that you produce, then you would have X amount produced minus a 0.1 times X for the amount that you use internally. And that amount would be the amount that actually makes it to the market. Now, in general, what we're going to have is some specific demand that we want to meet will be the total amount that we produce minus the amount that we use internally. The amount that we use internally will always be some multiple of X, the amount that we're producing. So in other words, it's going to scale linearly with the amount of produce that we actually make. So the way that I phrased that in the previous part was just to say that we're going to use maybe 1/10 of a gallon of gasoline for every gallon that we actually do put out to market. So this MX term is going to represent the total amount that we consume internally, and M can be different in different situations. But let's think about it this way. So let's just say that M is arbitrary for now, so we won't pick a specific value for M. Let's say that we know how much demand we have. So we know the demand numbers that we want to meet, and we know our internal costs. So we know D and we know M, and we're trying to figure out X, the amount that we should actually produce. So if we wanted to figure out our production, we could just solve this equation for X. And the way that I would do that is I would probably just factor out an X from both of these. So I'm going to factor out an X. And for a reason that I'll show you in just a second, I'll factor it out on the right. So if you factor out an X from the first term, you'll just get a 1. And if you factor out an X from the second term, you'll have this minus M. So this is the same equation, just rewritten with X factored out. And then if I wanted to isolate X, I can finally just divide both sides by this factor 1 minus M. So in this one-dimensional case, what we'll get is that the total production that you should have in order to meet your demand would be D divided by 1 minus M. So that's what the situation looks like whenever you have this one-dimensional case. And the Leontief input-output analysis does the same sort of analysis except this time you have multiple industries. So you can have 2 or 3 industries that all use each other's products somewhat internally. So for example, maybe you are talking about oil and gas. If you want to get a certain amount of oil to the market, then maybe you use, maybe I'll say oil and electricity just to sort of diversify. Maybe to get a certain amount of oil to the market, you need to use some oil and some electricity. And to get a certain amount of electricity to the market, you also are going to need to use some amount of oil and some amount of electricity. This is the model that you would use in that case. It will tell you exactly how much you need to produce in sort of raw amounts in order to meet some final demand. And in accordance with the notation that I set up before, M is going to represent the sort of input-output amounts. That would be the matrix that describes the costs for getting a single unit of each of these industries out to market. X is going to represent the total production, and D is going to represent the demand. And the analysis will be done similarly. So it's still going to be true that your demand is equal to the total amount that you produce minus the amount that gets used up internally for each of these industries. But this time, these equations are in terms of matrices rather than just scalars. So this is a matrix equation. But we're still interested in finding the total production matrix X. So we want to know how much should be produced for each industry. So this would tell us the amount from industry 1 that needs to be produced, so maybe the amount of electricity that we would need to produce, and then X2 would be the amount of oil that we need to produce, for example, to meet these demands from the oil and electricity industries. So we have a similar setup, but this time our equation is in terms of matrices, and we would still, if we wanted to solve for X, we would still want to factor out an X, but notice that X is being multiplied by M on the right. So if we wanted to factor out this X, I would need to factor it out on the right, and I can think of this as being an I times X, because the identity times X is just X, minus M times X. And we know from our distributivity law that I can factor out an X on the right side here, and I would get I minus M times X. So that's what this line down here says. D is equal to I minus M times X. And now we want to essentially divide by I minus M. Remember that I is the n by n identity matrix. We want to divide both sides by that, but remember that matrix multiplication is a little bit finicky. It cares about which order you multiply things in. So what we would actually do is we would multiply both sides of this equation on the left by I minus M inverse. So we would get I minus M inverse times D is equal to I minus M inverse times I minus M X. And I minus M inverse times I minus M, these will cancel to just be the identity matrix by the properties of inverses. So this right side would just be Ix, which is just X. So in other words, we end up getting this equation here that I minus M inverse times D will be the production matrix X. So in general, what's going to happen in these problems is we will know the amount of demand that the market has, and we'll know how much internal cost we have per unit that we manufacture. And we can use that information using the left side of this equation to come up with the matrix X, which is the production that we need in order to meet that demand. So you can think of this as being the basic equation that we're going to be using. The stuff above it is just the derivation of this equation. So this is going to be the relevant equation for these problems. And now let's look at an example. In this example, I'm not going to go through sort of a word problem. Instead, I'm just going to give you a specific matrix M and D, and we're trying to find the production matrix. So it says determine the production matrix given this input-output matrix and this demand matrix. So remember what we saw above is that I minus M inverse times D is equal to X. So we just need to compute I minus M inverse times D. And in order to do that, I think what I'm going to do is I will come down here to the side, as our scratch work to compute I minus M inverse. So I minus M inverse is going to be, now notice I in this case will be the same size as M. That's always going to be true. So I is going to be the 2 by 2 identity matrix, which is 1, 0, 0, 1. And then we're subtracting the matrix M, which was given to us in the prompt as 0.9, 0.1, 0.2, 0.7. And then after taking that difference, we want to invert. So this will be, if I just compute that matrix difference, in the top left corner, I would get 1 minus 0.9, which would be a 0.1. In the top right corner, I would have a negative 0.1. In the bottom left corner, I will have a negative 0.2. And in the bottom right corner, I will have a 0.3. So we want the inverse of this matrix. And now in order to compute this inverse, what I'm going to do is I will compute the inverse using the row reduction strategy, which we talked about, I guess, last week. So here we have the original matrix, which is what we want to invert. Whoops. And then remember, the strategy for inverting a matrix is we take the matrix that we want to invert, and then we append the identity matrix. So that's going to be on the other side of the augmentation bar. And then the goal is to row reduce the left side to be the identity matrix. Now, as usual, just like with solving systems of equations, I don't like having decimals in this matrix that I'm trying to reduce. So instead, what I'm going to do is I'm going to first multiply by the necessary numbers in each row in order to eliminate the decimals. So I'm going to multiply row 1 by 10 and row 2 by 10. But that row operation applies to the entire row. So we will need to take that multiple of 10 and apply it to the right side as well. So this would become 1, negative 1, 10, 0 as our first row. And then our second row will be a negative 2, 3, 0, 10. And now we can go through the rest of the row reduction strategy now that we have this matrix of all integers. So we have a 1 where we want it. And that means that we should focus on fixing the rest of the first column. So I want this entry to be a 0 now. To accomplish that, I would probably take row 2 and add 2 times what's above it. So we'll do row 2 plus 2 row 1 becomes the new row 2. So that's going to give me, actually, I think I'm going to come down here for that. So that'll give me that the top row is not changing. And the new bottom row is going to be the old bottom row plus twice what's above it. So this would be a negative 2 plus 2, which is 0. This will be a 3 minus a 2, so that would be a 1. This will be a 0 plus a 20, so that will be 20. And this will be a 10. So that's what I get at the end of that row operation. And then it looks like we're going to need one more row operation. So our first column is fixed. Our second column has a 1 where we want it. And that means that the last thing that we need to do is eliminate that entry negative 1. In order to eliminate that entry, what I would do is I would take row 2 and add, whoops, maybe I'll reverse those because I normally like to write the row that we're altering first. So I'll put row 1 plus what's beneath it. That will be the new row 1. So if you take row 1 and add what's beneath it, first let me just copy down the second row since that row is not changing. But if you take the old row 1 and add what's beneath it, you'll get a 1, a 0, as expected for this left side, and then this entry would be a 30 and a 10. If you just take row 1 and add row 2. And remember that once you finish with the row reduction on the left side, the matrix that exists on this right side is the inverse that you were trying to compute. So this matrix here is I minus M inverse. So I minus M inverse is 30, 10, 20, 10. And I can come back up here if I wanted to compute X. Remember, X is this I minus M inverse times D, so that would be the matrix 30, 10, 20, 10. That's I minus M inverse times the matrix D, which is 20, 60. Now this is a 2 by 2 times a 2 by 1, so this will be another 2 by 1 matrix. So notice that D and X will both be 2 by 1 matrices. And now if I compute this product, I would get in the top entry a 30 times 20, which is 600, plus a 10 times 60, which is also 600. So that would give me a 1200 in total. And then for the bottom entry, I would be multiplying the second row by this column matrix. So if I take this product, what I would get is 20 times 20, which is 400, plus 10 times 60, which is 600. So altogether, I would get 1000. And this is the matrix X that we're looking for. The interpretation of this, as we'll see in a second, is basically just that you would need to produce 1200 units from the first industry and 1000 units from the second industry in order to get a final demand, or in order to meet, rather, the final demand of 20 units and 60 units from those industries, respectively. So this is kind of an exaggerated example. The reason for this, like the discrepancy between these two, is just that notice that the first industry and the second industry are using a ton of their own product just to get a single unit of that product out to market. So that's why it's just because of that inefficiency in those two industries that there's such a large discrepancy between these two, the production matrix and the demand matrix. But in ordinary applications, we won't have such a large discrepancy. Whoops, I did not mean to delete that. Sorry about that. Let me see. I don't actually know how to get it back, so sorry about that. But in any case, I'll be posting the handwritten notes for this, so you'll have all of that information again. And in the next video,